Now, it's all great to be able to recognize series and parallel circuits, but it's not useful to us unless we know its effect on the system as a whole. So we need to know, how do series and parallel circuits affect the math of current and voltage? Now let's take a step back and talk about water again, okay? So right now we have a pump. This pump, we're going to call it an ideal pump. It behaves only at one point. We're always going to have 3 gallons per minute come out of here. We're always going to generate 12 bars of pressure, okay? So if we have just a simple arrangement, pipe coming in, pipe coming out, what is my resulting total flow and pressure, or head, of this system? Well, there's a pump and a pipe, so my flow is going to be 3 gallons per minute, and my pressure is going to be 12 bars of pressure. Nothing's changed. It's like, what's 3 plus nothing? It's 3. But now let's start adding some complexity to this. Now we have 2 pumps. Each pump is just like we described previously. It'll always put out 3 gallons per minute, and it'll always increase the pressure by 12 bar. So before we get into the math, are these pumps arranged in series or parallel? They're arranged in parallel. And I know that because if I were to view the water molecule coming in, it's going to come to this point, and it has options on which branch it wants to take before it rejoins for the total system. So anytime that there are multiple branches, that means it is in parallel. So now, in this case, what is our total flow going to be out of this system, and what is our total pressure going to be out of this system? Well, the flow rate, each can pump 3 gallons per minute, and it's pumping different water, right? The water that goes here is different than the water that goes through here. So if that's 3 and that's 3, so then that means that the combined total flow is going to be 6 gallons per minute. And the pressure, well, let's say this is pulling water out of a tank. Over here, we know the pressure here is 0 psi, or we're working in bar, I'm sorry. So this pump is going to boost the pressure up to 12 bar, and this pump is going to boost the pressure up to 12 bar. So if this area here is 12 bar, that means this total 12 bar is going to still only be 12 bar, because we're not adding the bar, we're just combining it together. All right, let's look at this again. Is this a series or parallel configuration? It is a parallel configuration. So, and we know that because a water molecule or an electron, if this was electricity, is going to have multiple flow path options. It doesn't all have to flow through the same pump. As a matter of fact, we know that it won't all flow through the same pump. So if we were to look at this system, what is my total flow and total pressure of this system? And again, we're just pulling it out of a tank here. So let's talk about flow. If I've got 3 GPM coming through here, 3 through there, 3, 3, I'm going to have 3 gallons per minute times 4 pumps is going to give me 12 gallons per minute. Now let's talk about the pressure. Each pump has 0 psi, 0 bar that it's starting from, right? Because it's pulling it in from this tank right here. Each pump is just bringing it over from one side to the other, increasing it to 12 bar. there's no addition of pressure in this system. So it's going to stay 12 bar. Okay, so let's take a look at this pump configuration. Is this configuration in series or is it in parallel? It's in series. So we know it's in series because the same water is flowing through each pump. If you're pumping the same water, you're not getting any benefit in terms of flow. So that means in a series arrangement, the flow rate for the whole system is just going to be the flow rate of an individual pump. Now what about head? If we were looking at this, pulling out of a tank, we got 0 bar right here. This is going to take it from 0 bar to 12 bar. But now this here is going to take it from 12 bar. It's going to add an additional 12 bar to it and put me at 24 bar. So my total system pressure of this arrangement is going to be 24 bar. One more here before we move back into electricity. So if we were to look at this system, we know that this is in series. So my flow of the whole system is just going to be equal to the flow of a single pump. And my pressure, pulling from 0, is going to be 12 bar, 24 bar, 36 bar, 48 bar. So now my total system pressure is just going to be the total addition of all of my pressures because my pumps are in series. So remember, when you're trying to figure out how to add voltage and amps, just think about water. It's a lot more intuitive and easier to visualize when you think about pressure and flow rate when it comes to parallel and series circuits. So just in summary, if we're talking about a parallel configuration of either water or electricity, current is added. Voltage or pressure just remains the same as an individual item. If we're talking about series, current and flow remains the same. Voltage and pressure are added together. So let's talk more about solar panels here and how we design our arrays. So we have an ideal solar panel. A solar panel behaves almost exactly like a pump. This solar panel is going to produce 12 volts all the time, 12 volts of pressure. And it has the ability to generate 3 amps of current. So now when we build a solar array for an 11SQF, we design it something similar to this. Now before you tell me what the math is for the volts and the current, tell me, is this in series or is this in parallel? It's in series. Now here, this is our load. It could be our light bulb. In this case, it's our pump. I want to know, what is the voltage that is applied to the pump and what is the current that's available to the pump? Now, just like with those pumps, I was drawing a little tank to define where 0 pressure is. In electricity, we do a little symbol like that to show it's called ground. And that's just a way we say, let's call this 0 volts. All right, so we're going to say we're at 0 volts. We're coming around here. And here we're going to get another 12 volts. Now we're at 12 volts. We're going to get another 12, putting us at 24. Going to get another 12, putting us at 36. Going to get us another 12, putting us at 48 volts on this system. So our voltage equal to 48 volts. Now what is our current going to be equal to? The symbol that we use for current is I. So if you see I, that means current. Now since this is all in series, the current is going to be equal to that which can be generated by a single solar panel. So my current is simply going to be 3 amps. Let's move on to another example. Here, are solar panels in series or parallel? They're in parallel. So what is the total voltage and current available to my load over here? Well, in order to do that, we want to first find the voltage of each string. We call this a string. Each item that's in parallel is a string. So the voltage is just going to be that of a single solar panel. Because if we come out of here, let's call this our ground. We're going to come out through here. We're going to get 12 volts before we're back onto the side over here. And same thing here. See, we're still at 0, 12. So it's the voltage is just going to be 12 volts. Now what's our current going to be? We're in parallel configuration. So the current is going to be equal to the sum of all of these currents in each little string. In each branch, we're going to add the currents together. Means that the current is going to be equal to 3 times 1, 2, 3, 4. Another way of showing this is we got 3 amps coming through that, which is going to combine with this. Now we have 6 amps right there because we got the 3 from here and the 3 from there, which is then going to combine with another 3 right there, making this 9 amps. And then when it combines with the flow from this guy, we're going to end up at a total of 12 amps. Now let's move on to a more complex system here, okay? Let's say that we're designing an RSI system or other large array. And due to the specifications of the pump, whatever component it is we're powering, we need a lot of power. So what is going to be the total voltage and current applied to our load in this configuration? So to do this, let's say, where are we calling our ground? Where's our 0 volts? I'm going to say that that's 0 volts. So we know 0 volts is all along this whole thing right here, okay? And we want to know, what's my voltage over here? Or what's the voltage across there? So we're going to go up the string. We're going to come up. We're up at 12 volts. We're going to come up again. We're now at 24 volts. We're coming up again. We're at 36 volts now. Now if I were to do that on any of the strings, it's going to be the same. You can't design the strings non-symmetrically. So my voltage total is going to be 36 volts because I just look at any string in the array and I find out what's the voltage of that string, and that will be your total system voltage. Now for the current, we want to find out, well, what's the current on each string? So now, what's the current that's going to be flowing through here? Well, if I forget everything else other than these 3 panels, I know that these panels in here together are in series, right? So I know that that is just going to be 3 amps coming through there. Now also, if I forget and just look only at this second string, these panels are in series with each other, okay? And so that's going to generate 3 amps also. At this point in time, I don't care about these other strings. I'm just looking at one string at a time. These panels are in series together. These are generating 3 amps. This is generating 3 amps. So those 3 amps are coming down, coming over here, merging with this flow. Now we're up at 6 amps. Coming down, merging with this flow. Now we're at 9 amps. Coming down, merging with these flow, which now is putting us at 12 amps. So our total system current is going to be equal to 12 amps. What I want to ask you guys is if I needed you to design an array for me, so this is my load, and I need it to have, let's say 36 volts. I'll say 24 volts. I want 24 volts, and I want 6 amps available to me. What's my array going to look like? If my solar panel, so if each gives me 12 volts at 3 amps. So I'm going to look at these numbers. I'm going to say each panel is going to give me 12 volts. My goal voltage is going to be 24. First, design for your voltage, okay? Take your total voltage that you need, divide it by your individual panel voltage. So 24 divided by 12 is 2. 2 tells me how many panels I need in series in order to operate this load. So let's go ahead and draw in 2 solar panels in series. Okay, so I've got this. But my voltage is good, but my current isn't enough, right? If I were to look at my current, I've got something in series, I get my voltage, but I only have 3 amps in my system. So what do I need to do to my array to get more amps? I need to add more amps by adding more panels in parallel. So we're going to add another string onto this. Now I don't need to redo my calculation of my voltage because adding things in parallel doesn't change your voltage, and I already know how many panels I want because I need to be generating the same voltage. Okay? So now I have 12 volts, 24 volts with 3 amps going through that. And again, I get 12 volts, 24 volts with 3 amps coming through there. And then when it combines, I have 6 amps flowing through my system. Let's do one more quick example of this. Let's say we're designing a large system, all right? My load needs to have 300 volts. 300 volts, and let's say we need to have, what's a good number? Say 50 amps. Okay? What is the configuration that I need to have? Well, we're using those same solar panels, so let's find out how many panels in each string we need. How many panels in series do we need? We're going to take 300 volts, divide that by 12, and that tells me I need 25 solar panels in series. I'm going to need 1, 2, 3, 4, 5, boom, 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 boom. I'm going to need 25 solar panels to be in this item, right? Now, I'm also going to need 50 amps. Each string is only going to produce 3 amps. So I'm going to take 50 divided by 3. 50 divided by 3 gives me 16.6 amps. What do we do? With amps, you always round up. So we're going to do 17 strings. So we're going to go 1, 2, 3, 4, 5, 6, 7, all the way out to 17 of these, okay? So ultimately, our array is going to be 25 by 17. All right, let's move on. Now, sometimes a solar array is going to be specified not in terms of volts and amps, but power. Electrical power is very easy to calculate, and that is accomplished simply by multiplying your current by your voltage. All right, so in that previous system where we said we had 300 volts, we had 50 amps, the total array power is going to be 15,000 watts. Watts are the energy of power, or you're going to see that as a 15 kilowatt system. All right. Thanks for watching, you guys. If you have any questions, feel free to talk to your engineers or talk to Charleston. We'd love to work with you guys and continue developing our teams.